The examples of triple integrals we've seen so far have all been over domains that are these rectangular boxes. But, you know, most shapes aren't rectangular boxes. Of course, often your integrals will be over rectangular boxes, but not always. There are other shapes out there. So let's look at an example where the domain we're integrating over isn't just a rectangular box. So let's integrate this function, x, y, z. So there's our integrand function. Let's integrate this function over the domain bounded by x equals -1, x equals 2, z equals 0, z equals 2, y equals 0, and y equals x squared. So this here is a picture of what this shape looks like. The x-axis is going this way. The y-axis is going sort of away from us. And then the z-axis is going up. So that's how the coordinate axes are situated here. This spot right down the middle, this, I guess, let me put it this way. This is the origin right here. Okay. All right, so as far as writing the integrand, well, our integrand is just this function. But remember, so we're going to put dv here, but dv is dx dy dz, or dz dy dx, or if you think about it, there are 6 orders that we could put the differentials in. So when we write dv here, we have to write dv in some order. We have to choose an order. And as with double integrals, choosing an order is the same as choosing how we are going to slice up this region. So let's suppose that we put dz on the outside. Okay, and we'll decide on the order of dx and dy later. So let's put dz on the outside. So when we put dz on the outside, right, our z coordinates are going from 0 to 2. So our z bounds are from 0 to 2. Of course, these are constants. Your outside bounds have to be constants. But putting z on the outside, what that means is the first thing we are doing is slicing this along a constant z value, right? Just like with a double integral, if you put dx on the outside and dy on the inside, when you have some region, the outside integral slices along a constant value of that variable. Same thing is going to happen for our triple integral. So if we put dz on the outside, we are slicing along a constant z value. So our slices are going to look like this. And then there's a hidden side back here, and then along here, and then it's hidden again, and then it joins up to this corner. Okay, so this shape looks, if we could sort of pull this shape out of the screen and turn it, this cross section would look like this. Okay, so this is the cross section that we're dealing with. Notice that this cross section is two-dimensional, right? When we take a three-dimensional shape and we slice it in one direction, we get a two-dimensional cross section. So now for our inside bounds, we need to write down bounds that will describe this cross section shape. Okay, so let's see how to do that. Well, we could slice this vertically, or we could slice this horizontally. If we slice this horizontally, our cross sections will be two separate pieces like this. That seems really clumsy. That seems like a bad idea. Probably not impossible, but definitely annoying. So let's not do it that way. Instead, let's take this shape, and I'm going to try to draw it a little better this time. Let's take this cross section shape, and let's slice it up vertically. Because if we slice it vertically, the top of every cross section is on the parabola, and the bottom is on this line down here. Okay. So slicing vertically is better. That means we have one slice for every x coordinate, right? These red slivers are going this way. Right? So there's one sliver for every x coordinate. So that means the next integral we should do is the x integral. Okay. So what x coordinates do we get? Well, the furthest left spot here is at x equals -1. And the furthest right spot is over here. That's at x equals 2. And we do need to be a little careful because I've drawn one cross-section. So what we really need to do is think about all of the cross-sections, right? There's another cross-section up here, and we have to ask ourselves, as we move from cross-section to cross-section, do the extreme x values change at all? And for this shape, fortunately, the answer is no. For every cross-section, the furthest left point is at x equals -1, and the furthest right point is at x equals 2. So every cross-section has the same x bounds from -1 to 2. Okay, so we've decided on a z, which sliced this thing sort of front to back, which gave us this two-dimensional cross-section. Now we've sliced this two-dimensional cross-section sort of vertically to get these red slivers. We move along a red sliver by changing y values. So now we need to decide at the bottom and at the top, what is y? And in principle, remember, just like for double integrals, in principle, inside bounds can depend on outside variables. So we might have functions of x or z in these two bounds. In this example, we won't, but we won't have both. But in principle, you could have functions of either or both outside variables. Okay, so how about the bottom end of these slivers? Well, if you think about every sliver sitting on every spot in this region, even on lower cross sections like this down here or upper cross sections like that, the lower end of each sliver is at y equals 0. So our lower bound is always 0 for the y integral. Okay, we're doing our y integral, so let's put dy in there. Now we need to think about the upper end of each sliver. Well, the upper end of each sliver is on the parabola, right? And so what is the parabola? Well, it's this parabola, y equals x squared. Note that this doesn't depend on z, but it does depend on x. So the upper bound for these slivers is y is x squared. So there's our integral. This is the double integral that we're going to calculate. Okay. Now that we have it written down, this triple integral is just like any other iterated integral. So I won't evaluate this one. Instead of evaluating this one, I'll let you grind through that calculation if you want. But instead of evaluating that, let's start over and think about what would this integral look like if we sliced this region up differently. Okay, so this way of doing it, I guess I should pause and say, if we were really interested in the value of this integral, this order would be a good order. So this is a good way to do this. So if we wanted to know what this was, this would be a good way to do this integral. But I want to see what happens if we slice this in other ways, just to give us some practice, I guess. Okay, so that's if we put the z integral on the outside. Notice along the way we did decide that putting the y integral in the middle and the x integral on the inside, we decided that was a bad idea because of how it made the slivers break up into two pieces. So let's not look at that order with dz, dy, and then dx, because we decided that's no good. So let's try, what if we put maybe x on the outside? How about y on the inside and z? Actually, let's put x on the outside, and we will decide later whether we want to put z next or y next. Okay, so since we're putting x on the outside, we have to decide overall on this entire region what is the largest and smallest x values. But, you know, this as we noticed before, this region goes from x equals -1 to x equals 2. That's what these two are saying. So our x integral, our x bounds are from -1 to 2. Okay, so what would a slice for constant x value look like? Remember, we're going to take a slice at a certain x value. So one typical slice is like this, and then there's a hidden side hiding back there, and then a hidden bottom side. Okay, so that slice looks like just a rectangle. That seems okay. If we draw another slice over here, there's the front edge of the slice, the top edge of the slice, the back edge, and then the bottom edge of the slice is hidden from us, but it's along there. Notice that slice is also just a rectangle. Right? Rectangles are good. We like integrating over rectangles. The bounds of rectangles are easy to write down. So, in fact, they're easy to write down in either order. So we could slice these rectangles in either order. We could put dz, dy, or dy, dz. Either one would work out equally well. For variety, let's do y next. So the way I've drawn this diagram, I've sort of imagined taking this edge, this front edge, and putting it here. And the reason that I have visualized it that way is because it requires turning this slice as little as possible. So doing it that way, the positive y-axis is going this way, and the positive z-axis is going that way. Okay, so if we put our y differential next, that means we're choosing a particular y value, which means our slice is going along that y value. Okay, so along this, so now we have to decide what y values give us vertical slices. Okay, so where do these red slivers live up in our three-dimensional picture? They are like this. Okay, so what y values give us vertical slivers? Well, the smallest y value is when we're at the front of this region, and that's y equals 0. Oops. That's y equals 0. So our lower y bound is 0. Our upper y bound is sort of the rear back here, and that's, well, that's on the parabolic cylinder thing, which is y equals x squared. So our upper bound is x squared. Okay, and then finally our z integral, well, along every vertical sliver, the bottom is at z equals 0, and the top is at z equals 2, because, well, look, from z equals 0 to z equals 2, right? So, like that. And so z is here, and our integrand is x, y, z. This also seems like a perfectly fine order. Right? So if we actually wanted to calculate this integral, this order would be a good order. So we looked at one order where z is on the outside, one where x is on the outside. Let's look at one where y is on the outside. So let me clean up my picture a little bit. Let's see, how much room do I actually need? This is probably good enough room. Okay, so if we start over, just for practice, and put our y integral on the outside, right? The y-axis is going, positive y-axis goes backwards, right? So if we draw a typical cross-section for constant, before we get to slicing in this direction, we should write down the bounds in this direction. So on this entire region, what is the smallest y value? Well, the smallest y value is at the origin here, which is y equals 0, right? This curve here. What is the largest y value on this entire region? Well, the largest y value is way back here at this point. So that is, let's see, this spot here is where x is 2 and y is x squared, so this spot is at y equals 4. So we're going to need to integrate from 0 to 4. Okay. So now let's draw typical cross sections along a constant y value. So now we're imagining we're at a constant y value. So the cross section at this y value is, well, there's the front edge of it, there's the top edge, and then, well, then the cross section kind of stops, but then over here it picks up again. Right, and then there's like this. I didn't quite get the sides looking just right. Let's see. Should have gone from this side. There we go. So this cross section, it's actually two separate pieces like this, which, I don't know, man. That doesn't feel too good, right? That feels like it would be hard. It would be hard to describe the inner bounds if our cross-section is in two separate pieces like this. So that makes me a little nervous. But in fact, it's even worse than that, because this is just one kind of cross-section. If we go far enough back, the cross-section is just this single piece over here. So this cross-section isn't two pieces, it's actually just one. So, I mean, how would we write our outside bounds so that sometimes the cross-sections have two pieces and sometimes they have one? We couldn't do it with a single integral. We'd have to have two separate integrals, right? We need to do one integral in the y direction from 0 up to whatever this spot is, which I guess is -1, because those are where this region of y values is where the cross sections are in two pieces. So this is y values from 0 to 1. And then past that, that's when the cross sections only have one piece. So we need a whole other integral for that, from -1 up to 4 dy. So that, because from y equals 1 to y equals 4, our cross sections are a single piece. But then still, for this first one, we'd have to write bounds on our inside integrals that give us these two pieces. I mean, that sounds terrible, right? So this order, this is a bad order. We should not try to do the integral this way, right? So the point of this whole example is to show you that if you have a shape that isn't just a rectangular box, you should stop and think about what is the best way to slice your region. You want your slices to be as regular as possible so that you can write as few integrals as possible. So always spend some time thinking about what order you're doing your slices in.